In this chapter, we're going to connect the concepts from last chapter regarding polynomial expressions, but we're going to use them to solve inequalities, which therefore we have to start this chapter by reviewing just how to solve inequalities of linear nature. So let's start right away with a couple quick examples. Number 1. Let's solve negative 7x minus 1 is greater than 13. If we solve this, just like before, we add 1 to the equation, and we divide by negative 7x. Remember, when you divide by a negative, divide or multiply. You must switch the signs. So therefore, x must be less than negative 2. If we graph this on a number line, it would look like an open circle at 2, negative 2, and then shaded to the left for all the values less than it. Let's do a second example. We'll spice it up a little bit. 2x plus 3 over 9 is less than or equal to x minus 1 over 6. The first thing I'm going to do is cross multiply. The 6 will come over here, and 9 will come over here. So we get 9 times x minus 1 is greater than or equal to 6 times 2x plus 3. Some people get confused by which way the sign should point. You're multiplying the 6 over to this side, and multiplying the 9 over to this side. Therefore, you do not change the order or the motion of the sign. Distribute. Get 6 times 2 is 12x plus 18 is less than or equal to 9x minus 9. And then real quickly, let's solve it. You get 3x is less than or equal to negative 27. X is less than or equal to negative 9. Again, on a number line, negative 9 close circle, and shade to the left. The last thing I would like to review is absolute value. The absolute value of a number represents the distance from x to 0. Therefore, if I say the absolute value of 4, that could be either negative 4 or 4 in terms of its distance. I'm sorry, if the absolute value of x equals 4. You can be 4 in either direction. You don't know which direction you're at, because both are a distance of 4 away. Therefore, we always have taken the positive and negative components of an absolute value sign. So let's do a couple quick examples. Number 3. Let's take the absolute value of 2x plus 3 is equal to 1. So to get rid of the absolute value bars, we have to set up two equations. 2 plus 3 is equal to 1, and negative 2x plus 3 must equal 1. The positive and negative parts must have a distance of equal to 1. Therefore, when we solve this, we get 2x is equal to negative 2, x equals negative 1. Over here, we divide by negative 1 to get negative 1. Solve it, we get x equals negative 2. On the next example, let's see the absolute value of x minus 2 is greater than or equal to 3. Again, same setup. The positive half must be greater than or equal to 3. The negative half must also be greater than or equal to 3. This is not how your middle school teacher probably taught you. In the end, they probably taught you to switch a sign, and they never taught you why you switch a sign. In reality, the absolute value, the positive and negative values of the distance, must be greater than or equal to 3. That's what the absolute value says. By writing this way, you'll see that when you divide by this negative, you get x minus 2 is less than or equal to negative 3, which is probably how your middle school teacher wrote it initially. I do it that way because in calculus there are some points where you want to see this positive negative half, and it becomes very important to know how to write an absolute value versus just following a procedure that works in this specific problem. So this answer here is 5, and this answer here is negative 1. Let's graph this on number line. Negative 1 would be a closed dot, 5 would be a closed dot. When x is greater than or equal to 5, and x is less than or equal to negative 1. Notice how the two shadings are away from one another. This makes this an OR problem. I have trouble remembering which one's OR and which one's less, and which one's OR. OR is always the non-inclusive one. This one does not include the middle, therefore it's an OR problem. Let's compare that to the next problem, where it is 2x plus 5 is less than or equal to 7. Again, if you write this in terms of its halves, it's positive 2x plus 5 is less than or equal to 7, and negative 2x plus 5 is less than or equal to 7. If we solve the first part, x must be less than or equal to minus the 5 divided by 2, 1. The second part, if you divide by negative, we get 2x plus 5 is greater than or equal to negative 7. So therefore x is greater than or equal to negative 6. If you see the graph of this, you'll see negative 6 and you'll see 1. Close dot, close dot. X is less than 1 but greater than negative 6. So you can see it's inside this. It's region inside. Kind of like a sandwich function. This is where it's AND. You could also write this as x is greater than or equal to negative 6, or less than or equal to 1. So, sorry. This implies the AND. So either you can write the word AND or write it like this. Both would receive full credit. If you do not write the or the AND, you would lose a point on a test or a quiz, because it's an important language that you must know. Again, if you write it as a sandwich function, that would suffice for the AND. And that concludes the first part of this chapter review. See you tomorrow.